When a new AI model drops, the question that matters for most teams is not the leaderboard score. It is whether your stack can run it reliably, what it costs at your traffic scale, and which shortcuts will break in production. Today, we connect that headline to the engineering trade-offs behind the hype. Consider this terrifying scenario. An intelligent chatbot starts giving users confidently wrong answers. You blame the model's training data or its prompt logic, but the root cause is a silent race condition in your database layer from 2008, buried deep in how SQLite handles write-ahead logging. This is not just a code bug, it is a hybrid failure where traditional software errors collide with probabilistic AI behavior to corrupt your entire system. Developers today often operate under the dangerous assumption that data storage is static and safe. We treat databases as passive buckets, assuming they simply hold information until we ask for it again. In legacy systems, this might have been true enough. But in modern AI pipelines, where a model's reasoning depends entirely on the context window fed to it from your database, any inconsistency becomes catastrophic. If a concurrency bug causes data to appear valid while being logically inconsistent, the AI does not crash with an error message. It hallucinates. It generates responses based on corrupted inputs, creating technical debt that persists for years because we assume the code generation tools are safe and the storage layer is immutable. This phenomenon has been formalized in recent research as a hybrid failure profile. In a study analyzing over 13,000 issues across 40 open-source repositories, researchers found that failures in modern systems are rarely random or purely probabilistic. Instead, they occur when traditional software bugs interact with LLM reasoning errors. A specific concurrency bug in the database layer does not just stop a query, it propagates state defects directly into the AI's token management logic. The result is cascading failure where standard engineering assumptions collide with the unpredictable nature of generative models, making debugging nearly impossible without understanding how your data interacts with intelligence at every step. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The illusion of safety in generated code makes this problem even worse. We increasingly rely on AI coding assistants to write our SQL and manage database interactions. A large-scale empirical study examined over 300,000 commits from thousands of repositories and found that nearly 1 in 5 issues introduced by these tools persists indefinitely. Crucially, 89% are not immediate crashes, but subtle code smells or structural weaknesses. These are the invisible time bombs in your architecture. Developers assume generated SQL is safe because it looks syntactically correct. However, unchecked quality assurance leads to accumulated complexity, where a 16-year-old assumption about how a database handles concurrent writes becomes embedded in every AI-generated function you ship. The root of this issue lies in the limits of traditional testing methods. We have long relied on automated tests that check for syntax errors or basic functional correctness. But these tools fail to catch dialect-specific logic bugs because they rely on manually written generators that miss complex edge cases involving concurrency. A new research framework called SQLite, which uses LLMs to synthesize SQL sketches and test them against major database management systems, discovered 50 previously unknown bugs in standard databases alone. This validates a critical point. You cannot test your way out of a state space explosion caused by unchecked assumptions about how two writes occur simultaneously. The solution requires modeling what actually happens when the system is under load, not just testing what the code does in isolation. This brings us to the core skill that separates junior engineers from principal-level architects in 2025 and beyond: assumption validation. A field study of AI product teams found 83 instances where design oversights led to system failure because developers assumed user behavior or storage consistency would remain linear when it did not. These are over-the-hood bugs, barriers caused by unchecked assumptions about how the underlying systems behave under stress. In our case with SQLite, engineers assumed the wall mode was a simple append-only log that guaranteed orderliness during high concurrency writes. When that assumption proved false due to a race condition dating back 16 years, the AI pipeline broke because it trusted data that looked valid but was logically inconsistent. The fix requires moving from testing syntax to validating assumptions using formal methods like TLA+. Think of this not as abstract mathematics or academic theory, but as rigorous stress testing for your system's logic before you write a single line of application code. You must model the database state machine explicitly to prove that concurrency holds up under load. By defining exactly what happens when two processes try to update the same record simultaneously, you can identify where your safety nets fail long before they reach production. This approach shifts the focus from fixing syntax errors after deployment to preventing systemic assumption failures at the design phase. As an engineer in this era of AI-driven development, you are increasingly responsible for systems where you do not control the logic of the intelligence layer, but you absolutely own the data integrity layer. If your assumptions about storage consistency are wrong, no amount of prompt engineering or model tuning will save your system from generating incorrect outputs based on corrupted inputs. The high-value skill now is identifying these systemic assumption failures and using tools like TLA Plus to prove that a database state machine behaves correctly under concurrency before you integrate it with an AI agent. If you ship AI-generated code without validating its interaction with legacy systems, you are inheriting silent technical debt. Studies show that nearly 23% of issues introduced by automated tools never get fixed, meaning your current projects may be carrying hidden failures from day one. The data integrity layer is no longer a passive utility. It is an active state machine with race conditions and timing constraints that must be rigorously tested alongside the AI logic you build on top of it. Treat every database interaction as a potential source of hybrid failure where software bugs feed directly into model hallucinations, and make assumption validation your primary defense against these silent system crashes. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.